Hello and welcome to MT3. In this tutorial I will be introducing the topic of linear operators. So this is an introduction, and you will find the material I'm going to be covering in this tutorial in Riley, Hobson and Bence section 8.2 linear operators. Of course, it starts from here. Yeah. Okay, now what is a linear operator? Thus far we have defined what a vector space is. You have an understanding of what these vectors in the space are, and remember we have generalized the concept of vectors to include things which are not just lines with directions. Okay, that's all fine, but we still don't know what to do with vectors. So let's say you've got a vector and you're in a particular space. Let's make this a two-dimensional space. I didn't want to go that way, so Control Z. Let's say this vector resides in this particular space. Okay, and we'll call this space, remember we gave our vector space a name, script V. So here's a vector A. And the space has basis vectors. Let's use a normalized orthonormal basis, so it's E hat 1 and E hat 2. That's our basis. So this is a two-dimensional space, so n is equal to 2, and our basis consists of two vectors, E hat 1 and E hat 2. Alright, now we have these vectors, we know how to add them up, we know how to multiply them by scalars, we know how to take the norm of two vectors, we know how to find their length. But thus far we haven't really learned how to transform one vector into another. So what could those transformations be? Let's take some examples. For example, you might want to make this vector longer or shorter, or you might want to rotate it by some angle keeping its length the same, or you might want to project it. Now by projection what I mean is let's say you project it onto the E1 hat axis, then this vector in its projected form becomes that. Or you could project it onto the other axis, in which case you will get this as a projection. Or you could project it onto any axis. For example, if you just choose a random axis here, the projection could happen onto that axis, and this would be your vector. Now rotations, projections, these are examples of linear operations on a vector space. Now what a linear operation does is it takes every vector in a vector space and converts it into another vector. Now if you're so let's have a look at the rotation example we had earlier. So if I go back and just remove these projections from view. Alright, now the rotation example took a vector A and converted it into a vector, let's say we rotated by a certain angle, and now we have another vector B, and this is some angle theta. So every vector gets rotated by this amount, by this angle theta, into some other vector, but the vector space itself remains the same. It's still a two-dimensional space. You just have mapped each vector into another vector. Projection, on the other hand, changes the dimension of the space. If I project every vector in this space onto this axis here, oops, and what I would end up then is a space of vectors which reside only along this axis, the E1 hat axis. Now what I've done then is converted a two-dimensional vector space into a one-dimensional vector space. So we could have linear operations which changed the dimension of the space. and projection is one such way of getting this done. So what is a linear operation and a linear operator, and why, in fact, why is it even called a linear operator? So let's put some definitions down. And now I am going to be using the definition from Riley, Hobson and Bence, so let's write it down here. So a linear operator A, and I'll use a script with a hat. So we'll denote all our operators with a script letter and a hat on top. A linear operator A on a vector space V associates every vector x which belongs to this vector space with another vector y which could belong to an other vector space. I'm going to call it V prime, such that, and this is written as, let's change color here, y is equal to a hat operating on x. Okay, now why is it called a linear operator? And so there is a such that for all vectors A belonging to V, actually it's A and B, so like that, for all A comma B belonging to the vector space V, and scalars lambda and mu belonging to our complex numbers, A hat operating on the linear combination lambda A plus mu B is equal to lambda times A hat operating on A plus mu times A hat operating on B. Now, because these operators A, when operating on linear combination, can be written as a linear combination of the operators operating on each vector in that combination, this is where the term linear operator comes in. It preserves the linearity of the space. Okay, so let's summarize. A linear operator A is some operator, and we've given I've given you examples of a rotation or a projection, or you could even have the identity operator. The identity operator A would take every vector in the space V and keep it the same as it was. So, for example, the identity operator, we'll call that I. It takes x, I operates on x, and it gives us x. In other words, it takes the vector space V and it transforms it into itself. There's no change here. The rotation operator rotates vectors and it keeps the space the same. The projection operator projects every vector onto a subspace. Now, this is a technical term, but a subspace is a space contained within a space. So in 3 dimensions, a plane is a subspace of 3-dimensional space. A plane has 2 dimensions. It's contained within the 3-dimensional space. So a projection operator reduces the dimensionality of the space. And we'll call that p beta hat operates on x and gives us a y, where x would belong to V and y to another space V prime. And if x has this space has dimension n, then this space would have dimension m, where m is less than n. Okay, so those are examples of linear operators. What we will do next now is demonstrate how a linear operator can be represented. So once you've got a basis set defined for your space, a linear operator can be represented as a matrix. And therefore all matrix operations on vectors can be thought of as a linear operation operating on a vector space. Okay, but that's in the next tutorial. So that was our introduction to linear operators, and I will stop here. Thanks for listening.